Topics in the History of Mathematics, MA 290. Cassette 4, Side 2. Desargues Projective Geometry, an explanation by Jeremy Gray of the course team. In this cassette, Jeremy Gray will talk you through some of the material on the geometry of Desargues and of some of his successors. You'll find it illustrated on pages 17 to 19 of Unit 7. So you should have Unit 7 in front of you now. Open at page 17. And also have your cassette notes with you. You'll find it useful to have a pen, paper and ruler as well. When you've got everything ready, turn the cassette back on.
We begin in figure 9, with a picture of a cone and two sections of it, one of which is a circle and the other simply called a general section. In this case it's an ellipse. Desargues' essential insight was to realise that if light shines from the vertex V of the cone, every conic section appears as a shadow of a circular section. And so somehow one should be able to derive properties of the general section by just considering the circle, which is the easiest case to consider. Desargues, in fact, spoke of the two figures being related by joining the points of one to the points of the other by lines through the vertex, and I'm just asking you to think of those lines as lines of light. Having had this idea, what did Desargues have to do to make it work? You can see the first problem that arises if you look at figure 10. Imagine that there is a point source of light at the point V. On the screen on the left, you see a picture of three lines meeting at P. The question is, what does the shadow of such a configuration look like? Well, they can cast a shadow which gives the configuration of the lines on the middle, tilted screen numbered 1. But there is a problem when the screen is put in the position numbered 2, on the far right. That screen has been tilted until it is parallel to the plane defined by the vertex V and the line QP. Can the line QP cast a shadow on this screen? If you have a desk light handy, you might like to conduct a modest experiment until you feel able to give your answer. The answer must be no, because the light from V that passes through QP, being parallel to plane number 2, never meets that plane, so no shadow is cast. Now, it's most awkward if a configuration of 3 lines is going to seem sometimes, after it has been projected, to consist only of 2 lines. Desargues' solution was to say that the configuration on screen number 2 really did consist of 3 lines, but one of them was the line at infinity. He remarked, with more honesty than helpfulness, that this was incomprehensible, but reason compelled him to deduce it. In fact, this idea of considering infinite figures on a par with finite ones is not just forced on him, it's one of the key ideas in the whole of his work. So we must just follow him here, trusting in his own admirable courage. If you turn to figure 11, you'll see another problem he was confronted with. Up to his day, geometry had dealt preponderantly with lengths. One spoke of 2 line segments as being the same in size, or of one being bigger or smaller than the other. But figure 11 makes it clear that the shadow of a line segment can be of a different length than the original, and, which is much worse, the 2 unequal segments can have equal shadows. The shadows of A and B, for example, are of equal length. They appear as A' and B', although A is clearly much larger than B. So this destroys any hope that Desargues could work with the most basic concept in Euclidean geometry, the concept of magnitudes along a line. You might think that this would have left him with nothing to build on, but Desargues knew some relationships would survive projection, because he knew, from his interest in perspective drawing, that accurate, lifelike copies of originals can be made. because some drawings of a figure are plausible, while others are not, there has to be some mathematical relationships between the original and its copies which distinguishes correct from incorrect versions. Indeed there are, and books on perspective were full of geometric constructions which enabled you to get it right. And of course it was well known that a pair of parallel lines in a plane could well appear as a pair of intersecting lines in a picture. So the sort of thing that happened in Figure 10 was no surprise to anyone with an interest in art. But the practical manuals on perspective didn't contain mathematical formulae. Desargues, with his interest in proving theorems by the idea of shadow projection, needed to find a substitute for length. The unit doesn't show you what Desargues actually came up with, which was a complicated configuration of 6 points on a line that he called 6 points in involution. We don't need to look at this now. We've put the definition of the thing in the cassette notes. The important thing to remember is that any time Desargues found 6 points related in this way, he had 6 points whose shadows were always related in that same way. It's what we call projectively invariant. When 2 pairs of his 6 points in involution coincided, he was left with just 4 points, and he called this the case of 4 points in involution. You can see a case of 4 points in involution in Figure 13, where we've also lapsed into a bit of a muddle about whether line segments have direction as well as lengths. Is CA the same as AC, or is it minus AC? Because CA goes in the opposite direction to the other segments, you might want to put a minus sign in the formula to make it say dB over CB equals minus dA over CA. That would accord with modern practice, but Desargues had no clear view on the matter. Desargues needed to know that 4 points in involution always cast a shadow of 4 points which are in involution, but that followed automatically from his treatment of 6 points in involution, and we've illustrated it in Figure 12. It means that being 4 points in involution is another projective property. Desargues also needed to know what happened when, whether by accident or design, a shadow of one of the 4 points was sent to infinity. That turned out to be rather nice, as you can see in Figure 13. When B goes to infinity, A moves to become the midpoint of DC. What's good about that? Well, apart from its intrinsic elegance, Desargues is in a situation where there is nothing he can say about 3 points, but a lot he can say about certain sets of 4 points. He would like to be able to go from any set of 3 points to these nice sets of 4 points. That's where this rather fine observation comes in. For knowing this special case, where B is at infinity, Desargues could then give a general construction which, confronted with any 3 points, A, C, and D, found a 4th point, B, so that A, B, C, and D were now 4 points in involution. We've put that construction into the notes. I mentioned earlier that Desargues was well aware of the practical tradition in mathematics. He was also well aware of the Greek classics, notably Apollonius's conics. In that work there are numerous occasions when 4 points in involution occur, although not, of course, under that name. One of the most important of these is shown in Figure 14. Perhaps you remember it from Unit 4. It was one of Apollonius's results we looked at then. But let's look at it again. Apollonius's result, which Desargues knew perfectly well, was that the 4 points T, R, I, and R' are 4 points in involution. So 4 points in involution do occur naturally in mathematics, and Desargues' interest in them is not artificial, nor does the concept originate with him. Now let's look at what is undoubtedly the most important result in Desargues' rough draft on conics of 1639. We've made a stab at it in the 2 parts of Figure 15, so let's build up the first diagram now. Locate the 4 points B, C, D, and E, and the quadrilateral through them. The sides BC and ED are extended to meet at N, and the sides EB and DC to meet at F. The diagonals, BD and CE, meet at the point R. You now have a figure consisting of 7 points and 6 lines, called a complete quadrilateral. The theorem applies to this configuration and any line, L, that crosses it, such as the one in our figure. Since you have 6 lines other than L must cut these lines in 6 points. And the theorem Desargues discovered was that these 6 points are 6 points in involution. We've called them P1 to P6. P1 is where L meets BD, and so on. For example, P4 is where L meets EC. Now we're going to investigate what happens when different positions are taken for the line L. It might help you if you take your ruler to the figure and move it about, starting with it on the line L and finishing up with it passing through R and N. My question is, what finally happens to the pair of points P1 and P4 in this process? Where are they when L passes through the points R and N? Well, the pair P1 and P4 coincide at R, because when the line L coincides with Rn, it meets BD and EC at R. Now for a similar question. What happens to the pair of points P5 and P6 when the line L coincides with Rn? They too coincide, this time at N. So what sort of a configuration of the points P1 to P6 on the line Rn are you left with? You're left with 4 points, and since you began with 6 points in involution, you must now have the special case of 4 points in involution. Now we come to the second diagram in figure 15. Start with the conic. An ellipse will do as shown, or any conic section in fact, and locate the 4 points B, C, D and E, and see that you have a complete quadrilateral as before. You might find it useful to make a careful copy of this figure now, before we proceed any further. Notice that you have 3 pairs of lines in the figure, the pair through F, the pair through R, and the pair through N. The theorem applies to any 2 of these pairs, and it asserts that any line which crosses the figure meets the conic and the 2 pairs of the 6 lines you have in 6 points in involution. In our figure, we chose the pairs of lines through F and N, so spend a minute or 2 making sure you know where these 6 points actually are before I ask you a question about them. With our choice of labels in figure 15, we've ignored the pair of lines through R. So I'd like you now to denote the points where L meets BD by P7 and where L meets EC by P8. Now, I'd like to ask you what happens to the 6 points P2 to P5, P7 and P8 if the line L is moved to pass through R and N. Well, you get 4 points in involution, 2 of which lie in the conic, and the other 2 of which are R and N. It's in proving this theorem that Desargues displayed his clearest grasp of his projective method, for he observed that it was enough to prove it for a circle, and then it followed automatically that it was true for any conic, because all it involved was concepts which were invariant when taking projections. You can read his convoluted expression of this marvellous idea as entry 11C3 in the source book, if you wish, but perhaps not now. You can get a glimpse of the way Desargues differed from Apollonius if you follow through the next exercise. Using the ellipse in the cassette notes, and following up the first part of my instructions which are repeated there, I'd like you to draw the complete quadrilateral BCDE on the picture of the ellipse. Do it in such a way that the conic, the points F, R and N, and the line RN stand out. Now do the second part. Draw through the point F a line meeting the conic at 2 points, P2 and P5, and the line RN at the point J. So don't draw this line to pass through R. Desargues was able to show that this gave him, and therefore gives you, 4 points in involution. You can see this more or less as he did, by starting with his result about 6 points in involution, when the line L is the line F, P2, J, P5 that you've just drawn. That gives you 6 points in involution. So mark them on your sketch. They lie on L, obviously, where it meets the conic. That gives you P2 and P5. And F, which we must count twice, because we're interested in where the line L meets the lines BE and CD. But that happens to be F, both times. And then a point on ED, called P3, and a point on BC, called P4. Now think of the lines EDN and BCN as blades of a pair of scissors hinged at N, and close them shut along the line RN. You might like to look at my picture of this in the notes. What happens when the lines EDN and BCN finally coincide along RN? When these three lines coincide, the point P3 coincides with the point P4, and they both lie on top of the point J. So when the three lines coincide, the original 6 points in involution have become 4 as claimed. This result was known to Apollonius, but he didn't think of proving it this way. Perhaps that's why he didn't find what Desargues did, the simple construction for a tangent to a conic through a point T lying outside it. That is, given a conic and some point T lying outside it, what can you do to construct lines passing through T which are tangents to the conic, as in an illuminating figure 16? If you have a real yen for these things, you might be able to work it out now. You have all the necessary ingredients, but I'll be giving his construction in a moment. Let me give the game away first. In figure 15, how would you find tangents through the point F to the conic? It's a fair guess that they will touch the conic at the points where the line RN crosses it, and that turns out to be true. So if only the conic and the point F are what we are given in the first place, we need to construct the line RN. What Desargues saw, but Apollonius did not, is that you can do this by constructing a suitable quadrilateral with its vertices on the conic. My picture of this is in the notes. So, to draw the tangents through T in figure 16, draw any two lines through T that cut the conic. Call them TEB and TDC. Join EC and BD, letting them meet at R. Join ED and BC, letting them meet at N. Join RN, letting the line RN meet the conic at Q and Q prime. Then TQ and TQ prime are tangents through T to the conic and touch it at Q and Q prime. That's all I want to say here about Desargues' achievement. It's a remarkable blend of two kinds of erudition, the practical and the classical kinds of mathematics. A substantial piece of visualizing, and, in its original at least, a wretchedly bad piece of writing. I hope it hasn't been so hard here to see what it was he did. Naturally, one wonders how it all went down, and you can see in the unit the reception it met with. I want to finish with one last mathematical excursion. This relates to Lahir's theorem, called after the French mathematician who discovered it. We've just seen in figure 16 that given a point T lying outside a conic, there's an interesting line you can construct, QQ prime, which joins the 2 points where the tangents from T touch the conic. Let me call that line the polar of T. Now turn to figure 19 on page 21. In figure 19, I've shown 3 different points, Q, P, and R. The tangent lines from each of these to the conic, and their polars. Look just at the point P first and locate the line LP. That's what we're calling the polar of the point P. Now locate the polar of the point Q. It isn't labelled, but it's the line going roughly northwest, southeast. Now locate the polar of the point R. It isn't labelled, but it runs southwest, northeast. Lahir's theorem is a pretty one. It says that if the points P, Q, and R lie on a line, then their polars all meet at a point. We shan't discuss the proof, but it's an elegant result, and you'll see in Unit 15 that when this material was rediscovered in the 19th century, it was to have a dramatic impact. That concludes this cassette, so you should now resume your study of the unit at a convenient time for you. Since we've left ahead for a moment, I'll remind you that your reading starts again on page 20.